Welcome, deep divers. Really excited about today's topic. We're looking at something huge for humanity's future off-planet. Specifically, how do we set up shop on the moon, like sustainably? Visiting is one thing, living there, well, that's the real challenge. So our mission today is to unpack some fascinating science. We're diving into how we might get vital stuff, water, oxygen, even metals, straight from lunar dust. And our source for this is an excerpt covering lunar resources, water, oxygen, and metals from regolith.
Yeah, and it's so important because, relying on Earth for everything, just launching water, air, materials, it's incredibly expensive. It's just not sustainable long term. This research, it really offers a way around that, a path to becoming less dependent, making a real lunar base seem, well, actually possible.
Okay, less dependence, more self-sufficiency. So how? Let's get into the science. The core idea sounds almost like science fiction, but it's happening in the lab. Scientists have pulled water and oxygen from a mimic of lunar dust, regolith.
Exactly, regolith. That powdery top layer you see in all the moon photos. And the method they're using, it's called molten salt electrolysis. It sounds complicated, but think of it like this. They take the fake moon dust, dissolve it in special salts that are already melted super hot, obviously around 950 degrees Celsius.
950 C. Wow. How do they even get it that hot?
Well, that's the clever part. They propose using concentrated sunlight, just focusing the sun's rays, which the moon has plenty of, at least during its day.
Okay, so you've got this super hot soup of molten salt and moon dust. You run electricity through it. What actually comes out?
The big one is oxygen. It gets released from the metal oxides in the regolith, essential for breathing, obviously, but also for rocket fuel. And you're left with metal alloys as a byproduct. Things like iron, aluminum, silicon mixes.
So construction materials, potentially?
Potentially, yeah, free metal, basically. And crucially, they also showed that if you add hydrogen into the mix, you can produce water.
Ah, okay, so water isn't a direct product. You need hydrogen first.
That's right. Oxygen comes straight from the regolith, but for H2O, you need that H. And that hydrogen, for now at least, would likely need to be brought from Earth.
Gotcha. Still, oxygen metals directly from dust using sunlight. That's the aha moment, isn't it? Using what's already there.
Absolutely. It's about in situ resource utilization, or ISRU. Living off the land, essentially.
Which brings us to the really big question. Lab success is great, but can this actually work on the moon on a large scale?
Well, the study's definitely optimistic. The key ingredients, regolith and sunlight, are abundant, like we said. And concentrated solar power could generate those high temperatures needed, especially during the long lunar daytime, which lasts about 2 Earth weeks.
So you can kind of picture it, can't you? These big solar concentrators, maybe arrays of mirrors, focusing sunlight onto reactors, processing the dust.
Yeah, churning out oxygen, maybe feeding it into habitats or propellant tanks.
It makes it feel much more real. But let's be realistic. Nothing in space is ever that easy. What are the big roadblocks, the cosmic hurdles?
Oh, there are definitely challenges. Big ones. First off, just running complex equipment in a vacuum with those extreme temperature swings, it's tough.
And the dust itself, right. I've heard lunar dust is nasty stuff.
It's incredibly abrasive, like microscopic shards of glass. It gets into everything, wears down seals, damages mechanisms. Keeping machinery running smoothly in that environment is a huge engineering problem.
Okay, so equipment failure is a major risk. What else?
Power. What happens during the 2-week lunar night? You need continuous energy for this process. So massive energy storage solutions would be needed, or maybe locating near a permanently lit crater rim, if possible.
Right, the long night is a killer for solar power.
And then there's the hydrogen logistics we mentioned earlier. If you want water, you need hydrogen. Transporting that from Earth adds cost and complexity, until, maybe, we can source it from lunar ice deposits if they're accessible and usable.
So it's not just one problem, it's a whole set of interlocking environmental and engineering challenges. It's operating in a fundamentally hostile place.
Exactly. It requires solving problems across physics, chemistry, engineering, material science.
Okay, so stepping back from the technical details, what's the bigger picture here? Why should you, listening right now, care about melting moon dust?
Because if this works, it fundamentally changes our relationship with the moon, and maybe space travel generally. It means critical resources, water to drink, air to breathe, fuel for rockets, metal to build with, could potentially be produced locally.
Right there on the moon.
Right. It dramatically reduces our dependence on Earth. Think about the cost savings, the logistical simplification. It makes a permanent lunar base, maybe even missions onward to Mars, far more feasible.
It's less like camping, more like homesteading.
Kind of, yeah. It's a foundational step towards humans actually living and working sustainably off-world, not just visiting, but staying.
So just to wrap our heads around it, the core idea is using sunlight and electricity to process lunar dust, unlocking oxygen, metals, and potentially water right where we need them.
And it really captures that spirit of space exploration, doesn't it?
Yeah.
Incredible scientific thinking, meeting head-on with really tough, practical engineering realities.
It does, and it leaves us with a pretty big thought, doesn't it? If we can genuinely start living off the lunar land, does the moon just become a stepping stone, a sort of refueling station on the way somewhere else, or does it become something more? Humanity's next permanent address, a genuine frontier, something for you to think about. Thanks for joining us on this deep dive.